Okay. Now, after having given a similar spiel in my other class, okay. All right. So, and you've gotten various emails from administration, and I'm sure at least some extent you've been following the news about what's happening with the novel coronavirus. Um, and so it's important we be prepared for anything, including this possibility. What if the university hands down an edict saying that classes must switch to being online, as other universities have already done. And it's something I've been thinking about how it would go. So I know this is something that's being contemplated at high levels. So we'll just see what happens. If I'm told something, I'm just going to send an announcement right away that of what's going to happen. Like, it could be something where you guys aren't coming here to class anymore. And so what I would probably do is still on the same schedule that we have. It's Monday, Wednesday, 4 to 5:15. But I would still come here if permitted, or from home if not, and just record a lecture and post it. And then we'll just try to figure out everything else from there. So, kind of a pain for the what I have in mind for final exam, coding option versus oral final. I have delivered oral finals remotely before, but that's been like for individual cases, not an entire class. And I've found out once you simply accept that there's going to be major disruption and get an idea of how you're going to handle it, it seems to be easier to do so. So, just all those emails that we get from USM mail out, I guess we have to pay attention to them now. Okay. And I just realized that I think I had broad discussion about the virus in this class already. So sorry if I sounded repetitive. I just totally forgot about that. But I was talking about it for the first time to my other class this morning. Okay. Now, so this section here, 11.1, Systems and Nonlinear Equations, is a direct follow-up to what I have been covering the last couple days. But fixed point iteration, Newton's method, Secant method, for a single equation. But so this section is kind of a bridge between that material that was kind of a review for some 460, 560 stuff, and the material that's going to come later. Because after this section, it's all differential equations from now on. Perhaps to this crowd, I should emphasize ordinary differential equations, not the PDEs that you're tortured with during the previous time slot. Okay. Although these numerical methods certainly are a foundation numerical methods for PDEs, but so in some cases when there's need to solve a system or as a system of ODEs, or maybe a single ODE is discretized to give a nonlinear system of equations. So instead of AX equals B, a linear system, you're having like f of x being 0, where x is a vector. Then how do we go about solving that? So these methods that I've been talking about, fixed point iteration, Newton's method, Secant method, have to be adapted to the multi-dimensional case. I actually have not given homework problems on this section, but some of these things are going to come up later. And if you choose the coding option for the final, and yes, not many people do that, but hopefully the number will be greater than 0. Then it'll certainly come into play there. Okay. So the problem that okay. So what is the problem that we're solving in this case?
So what is the chance of these classes getting online? Like out of hundreds, what percent?
Of us having to do that?
Yeah.
I honestly think it's pretty dang close to 100. But it's just a matter of when.
I know I went to some schools visit, like Vanderbilt.
Yeah.
And right after I left, a week after, they just suspended all the classes.
Yeah.
Also up there in Princeton and UCSD and stuff.
Yeah, and if you'd asked me this question a couple days ago, I probably would have given a lower number, just because the first universities that were making this change were in areas that were already pretty hard hit by the virus, like the Bay Area or Massachusetts. Oddly enough, I was in Massachusetts around the time that they were holding some conference that led to most of the cases in Massachusetts. So that was a close call. But then, like in Ohio, after they had 3 cases, the governor freaked and closed the state, basically. And Ohio State University in particular did that. So, what? Yeah, that happened this morning. Like on Monday, the provost here imposed a ban on all university-sponsored travel, which was a stronger reaction than I had seen in any university around us, which kind of pissed me off, honestly, because most of you know how much I love to travel. And
yeah, they told me that you cannot go to campus with it anymore.
Yeah. So, and I understand, though, having an abundance of caution. So, now that we have spring break, it's possible that you guys go off for spring break, and then sometime during the ensuing week, a provost might say, "Don't come back." And honestly, the challenge from my point of view is not about the classes. I feel like for the classes, especially since we have already had the only in-class test we're going to have, it'll feel pretty straightforward. Plus, I've taught online, so I'm not too worried about that. The real challenge is the many students that I do research with, that I meet with, twice a week or so, so how do we keep all that activity, that research activity, going when the students are not coming to campus? So we're to rely on technology and so forth to not fall behind. The students are having to finish their theses and dissertations and all that. So I'm just bracing myself for it, and I tell myself, like, these outbreaks, they happen at some point. They just come to an end. Like I'd read, I don't know how reliable this is, but what I'd read was that the virus cannot survive temperatures above 77 degrees, which it's going to be here in Hattiesburg for the next several days. It's going to be in the 80s. But then it blasts the air AC inside, and the virus is like, oh yeah. Experts have said that this is something that's going to drag on for like a couple months. And so we just have to hope to try to protect ourselves during that time. And then for those of us who are fortunate enough to, escape it ourselves and have our loved ones escape it, then there might be something approximating normal after that. So we'll see. So we'll see how right I am on that, about 100%. Okay, so what's the problem that we're going to be looking at? Find a vector x in Rn such that a vector-valued function, okay, and I'll call this x star, like I have been doing, is equal to the 0 vector. And I use bold to indicate anything that's a vector quantity. So F, you can think of as a vector field. So it maps Rn. So it maps an n-dimensional vector into another n-dimensional vector. Okay, so we've been dealing with case n equals 1 up to this point, and now we'll go with n greater than 1. Okay. So, and f of x, being a vector-valued function, has component functions that, so in case I need it for just notation purposes, so we have component functions f1, f2, I'll fill in the parentheses shortly, fn. So then x also will have components, since it's a vector in n-dimensional space. Okay. All right. So in other words, each one of these component functions has to be 0. So we're going to find x1, x2 up to xn n values that will make that happen for each of these. Okay. 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 So now what we're going to do is okay, look at the different methods, fixed point iteration, Newton's method. These we saw before in a one-dimensional case. And then this one is quite different, Royden's method. But you can think of it as a version of the secant method generalized to systems of equations. So once we see Newton's method, I'll be able to explain Royden's. Okay, so first, fixed point iteration. So we can rewrite f of x equals 0 as x equals g of x to use fixed point iteration, which the algorithm, of course, will be exactly the same. So that would be x k plus 1 equals g of xk. Whereas before, x naught is an initial guess. All right. So as an example of how we could choose g, I could say g is equal to x, let's see, minus some matrix A times f of x, where, where A is invertible. So what that means is if f of x is equal to 0, then g of x is equal to x. And if f of x is non-zero, then a times that vector will also be non-zero because of a being invertible. So this ensures that f of x equals 0 if and only if g of x equals x. So that we've seen this before in a one-dimensional case where I have like x minus some constant times f, and the constant had to be non-zero. Similar idea here. We just need it to be invertible. So anything that has a multiplicative inverse works. Okay. Now, if I recap, when did this converge in a one-dimensional case? All right. So in the all right. So in the 1D case, it's a short if g prime of x. Okay, that's weird. Oh, that's why I'm not in math mode. Okay. G prime of x is less than or equal to some constant L that is less than 1 on some interval AB, where that's known to have a solution or a fixed point. So I want to give a similar condition for this function g that applies in the n-dimensional case. So what would that be? We need... Okay, I'll define all this momentarily. Okay. So in a one-dimensional case, G has to map the interval AB into itself. Similar condition here. The function G maps a domain D, which is an n-dimensional space. So D is a subset of Rn. So it has to map this domain into itself. Okay, so mapping some domain into itself, that's what helps ensure that the function can have a fixed point at all. But what is this condition here? So this matrix, J sub G, is the Jacobian matrix of G. So it's a generalization of a derivative to n-dimensional space, a function of n variables that has n outputs. Okay, something went wrong here apparently. Oh. Oh, okay, I missed a brace somewhere. Oh. Way up here. Okay. Alright, so let me define the Jacobian matrix. Okay. So it's a matrix of all first partial derivatives of G, of a components of G. Okay, so partial G1 with respect to partial X1. So G1 is a component function, the first component function of G. And then take a derivative with respect to X2 and so forth until take a partial with respect to Xn. All right, so first row is partial derivatives of a first component function, G1, with respect to all the independent variables, all the x's. Okay. And then this continues like into the second row, all the partial derivatives of G2. So really the first row is a gradient of G1, second row is a gradient of G2, and so on. Oh, I just realized Use the wrong kind of dots in the book. I need to fix that. Okay. Okay. And finally, the last row, partial derivatives of Gn with respect to all the x's. Okay. So this generalizes the notion of a derivative to functions functions that map Rn into Rn. So, and here, the double bars, we saw this before with iterative methods. This is the norm of the matrix. Now, it could be any norm. It could be the one norm, infinity norm, whatever. So if it is bounded away from 1, then convergence is assured. Now, I want to emphasize both of these. This condition is sufficient, but not necessary. And really, it's the same condition, essentially. Because if you take a norm and reduce it to from some matrix quantity, but then you go to 1-by-1 matrix, the norm will always reduce to absolute value. So this condition is sufficient, not necessary. Okay. All right. So for instance, you could check the infinity norm of this matrix. Like if you look at the maximum row sum, that's the infinity norm. If that is less than 1, then you know that you'll have a convergence. Okay. Now, so this is similar to the condition for convergence of iterative methods for A, x equals B. Because those iterations have this form, m x k plus 1 equals n x k plus b, where m is equal to, a is equal to m minus n. Okay. All right. So this is an iteration of a form xk plus 1 equals g of xk, where here's a function g of x. So that would be equal to, if I multiply both sides on the left by m inverse, plus m inverse b. Okay. So that's a function g. So what is the Jacobian of this function g? Well, this is a linear function of, oh wait, that superscript k should not be there. Okay, because it's just general function g of x. This is a linear function of x. Well, the derivative of a linear function like ax plus b is whatever is multiplying x, that constant a. Here too, the Jacobian matrix of a linear function is whatever matrix is multiplying x. So the Jacobian is just m inverse n. And we had the norm of m inverse n being less than 1 is sufficient for convergence. And the spectral radius of m inverse n is necessary and sufficient for convergence. So that's in the case of a linear G. Okay. Now, I'm going to quickly take a look at an example where fixed point iteration is used. All right, so this system of equations. Okay. So x2 is equal to x1. What? Stop it. x1 squared. And we also have x1 squared plus x2 squared is equal to 1. Now, these are curves in two-dimensional space. What kind of curve is this? Like if I drew a graph of that, what would it be? Yeah, it's a parabola. Y equals x squared. And the other? Yeah, it's a unit circle. So if you take a parabola y equals x squared and the unit circle, these will intersect at a point. And so that would be the solution of this system of equations. So this system can be written in this form. I want x equals g of x. So I need to do some rearranging here. And that means I could take really the second equation and solve it for x1. Okay. And then I'll take the first equation. I don't need to solve it for x2. It's already isolated. So now this is of a form x is equal to g of x. So this is my function g in this case. So we have so x equals g of x, where g of x1, x2 is equal to that. Okay. So if I try fixed point iteration, I can. So we could try fixed point iteration on this domain. D is basically this square in the first quadrant. Because if I pick any point in here and substitute it into here, if I take a number between 0 and 1 and plug into both of these functions, I'm going to get something that's also between 0 and 1. So in other words, G maps this domain into itself. Okay. So I can choose some point in this square as the initial guess. But if I do that, actually, let's find out. I'm going to find a function g. So it's a function of x, like a vector x. And I'll return a vector where the first component is square root of 1 minus x2 squared. And the second component will just be x1 squared. Okay, so that's my function g. So I'll define my initial guess to be, I'll just choose the midpoint. Oh, hold on. Need a diary for this, so I'll just redefine. Okay. So now I can do x equals g of x. And let's see what happens. Okay. So I'm going to keep going and see if there's some kind of convergence. It's not looking too good, though. There's a lot of change. Like here, from 0.12 all the way to 0.8. It kind of bouncing around. So I'll just keep going for a while and see if something happens. Like here, it's at the upper right corner near 1, 1. And now it's at 0, 0. So it seems to. So now it just goes around the corners. So that's pretty awful. So it failed in this case. So we'd like to have some idea of why. So let's look at the Jacobian matrix. So that'd be a 2 by 2 matrix, where we take a partial derivatives of this with respect to x1 and x2, and then that's the first row. Second row is partial derivatives of this with respect to x1 and x2. Now, each one of these depends on only one of the x's, so that helps. That one partial derivative at each row is going to be 0. So, like, this has no x1 in it, so we get a 0 here. And this has no x2 in it, so we're going to get a 0 there. So 0 on the diagonal. And this will be 2x1. And the other partial derivative will be minus x2 over square root of 1 minus x2 squared. Okay. Now, here, x1 and x2 are allowed to be anything between 0 and 1. But notice I double it here. So we can see that for some x in the domain D, this Jacobian matrix will have a norm greater than 1. Okay. So for that reason, it's not surprising that convergence doesn't happen. So what we can do is, let's try a different G. Let's take these equations and isolate x1 and x2 differently. Okay. All right. So instead I'll do x1 is equal to square root of x2. That's from a parabola. And then x2 from a circle is equal to 1 minus x1 squared. Okay. Now what happens in this case, all right. Okay. So for the Jacobian matrix, all right, so let's copy this one and then change accordingly. All right, so I'm actually going to switch these rows. Whoops. Okay. Oh. Actually, that's not going to work so well. Hold on. Alright, so I'm going to have 0 again, and then I'm going to have 1 over 2 square root of x2. And then I'm going to have minus x1 over square root of 1 minus x1 squared, 0. Okay. Now, this can still have a norm that is greater than 1. But let's try it out. So if I redefine G, So I'm going to have square root of x2 and square root of 1 minus x1 squared. Okay. So now what we have is my initial guess. And now I will try this and see what happens. Seems a little better. Whoops. Whoops, I just caused it to start over. Dang it. Gotta be more careful with my arrow keys here. It's not bouncing around so crazy. It actually looks like it's converging. Just slowly. Okay. So one thing I want to check on is the Jacobian of G. If I look at my formulas, it's going to be 0 and then 1 over 2 times the square root of x2. It should be a comma, not a semicolon. And then the second row I have minus x1 over square root of 1 minus x1 squared and 0. Okay. So notice the norm of this is still going to be greater than 1 because it was minus 1.27. However, if I look at the eigenvalues of JG, notice that, well, they're imaginary, but they are, the spectral radius is less than 1. So near the fixed point, the spectral radius of Jacobian of G is less than 1. So similar to the condition for iterative methods as necessary and sufficient for convergence, having this here seems to explain why there is convergence in this case. Whereas if I look at the other Jacobian matrix that I had, at the same point, so that would be up here. Okay, so 0 minus x2 over square root of 1 minus x2 squared. And then I have 2 times x1, 0. And I look at the eigenvalues of this matrix. Here, the spectral radius is greater than 1 for the G that failed. So, just like with fixed point iteration for a single equation, we saw, and I showed an example of that last time, where if a derivative is greater than 1 in magnitude at the fixed point, you'll get divergence. It's called an unstable fixed point. Whereas if it's less than 1 at the fixed point, we tend to see convergence. Same idea here, applied to the spectral radius of a Jacobian. Okay. So for nonlinear equations, it's a bit more, especially systems, it's a bit more difficult to establish theory in higher dimensions. But at least we have some idea as to why convergence happens when it does, or why it can fail. Okay. So questions about this freaky example? All right. So now, let's take a look at Newton's method. Now, recall the formula for a single equation, and that would be xk plus 1 is equal to xk minus, and I'm going to write it in an unusual way, f prime of, all right, so a single equation of a form f of x equals 0. All right, so f prime at xk inverse, in other words, an ordinary reciprocal, times f of xk. All right. So now we see that for a system of equations, generalization is quite straightforward, in appearance anyway. F x equals 0 vector So all it is k plus 1 is equal to xk minus the Jacobian of f evaluated at xk. So all the partial derivatives have to be evaluated at xk. Inverse times the function f evaluated at xk. All right. So every iteration you have to solve a system of linear equations to solve this system of nonlinear equations. So dividing by a derivative in the one-dimensional case became solving a ax equals b problem in the higher dimensional case. So really we have xk plus 1 is equal to xk plus a vector, which I'll call sk. Sk being the step from xk to xk plus 1, where sk is the solution of this system of equations. Jacobian of f at xk times sk is equal to minus f of xk. All right. So all those methods that we've seen, like from Chapter 3 and Chapter 5, you'd use one of those to solve this. You would never actually explicitly form the inverse of a Jacobian. That's a big no-no, especially when we have a large system of equations. It's terribly expensive. So you evaluate your function f at xk. You evaluate all the partial derivatives of f at xk. Then the system is set up. Go ahead and solve it using these standard methods. And then the result, the solution, is what gets added on to your previous iterate to get your next one. Okay. Alrighty. Okay. And I have an example. It's a bit cumbersome to go through here, but all right. So Newton's method can be shown to converge quadratically, but can fail if the Jacobian is singular at the root, or the iteration can break down if the Jacobian is singular at xk. Because you're taking a matrix Jacobian evaluated at xk, and you're trying to solve a system involving that matrix. So if that matrix turns out to not be invertible, then you're done for. The only thing you can really do at that point is just choose another guess and try again. But the quadratic convergence observed in Newton's method under normal circumstances, where the Jacobian is non-singular in whatever domain containing the solution, generally will lead to quadratic convergence. And you still want to try to choose an initial guess that's close to the solution, if you can. Okay. Now, I had mentioned before a drawback of Newton's method. So it can fail to converge, and expensive per iteration due to evaluating the derivative, as well as the function you're trying to find a root of. So this is far worse for systems. And the reason why is not only expense evaluating n squared partial derivatives. So before, ordinary Newton's method for one equation, you'd evaluate this one function f of x, and then one other function f prime of x, so two functions. Now you have to evaluate the n component functions of f. All right, that's not so bad. But then also the n squared partial derivatives. And those could be pretty nasty. But then it gets worse. The n cubed expense of solving the system of Jacobian so Jacobian times s is equal to minus f. So that takes order n cubed operations, because you're dealing with an n by n Jacobian matrix. So what if it's a particularly large system of equations? Each iteration of Newton's method, you might not be performing many iterations because Newton's method converges quadratically, but each iteration is terrible expense. So we'd like to have some alternative, something that can still converge rapidly, maybe not as rapidly, but doesn't incur this terrible expense. And that's what leads to Royden's method. Okay. Seem to be missing the page I need. Okay. Okay. Found it. So just make sure I have this correct. All right. All right. So the idea behind Royden's method is that it uses an approximate Jacobian at every iteration. Okay. So let's see. Let me make sure I have. So I have a lot worked out here for like describes the first iteration, but I want to be able to correctly describe what happens for all iterations. Okay. E0Z. Okay. Okay. So in other words, it's still a Newton-like iteration. We're still solving a system at each iteration, but we're reducing the expense of coming up with this this matrix and solving this system. So it's still going to be expensive, but not as expensive. Okay. So first approximation, which I'll call A0. All right, so first time around, we do use the actual Jacobian. So Jacobian of f evaluated at the initial guess. Okay. Each subsequent Jacobian, AK, for k greater or equal to 1, satisfies the following. So the first condition is called the secant condition. So this is why this method is, in a sense, a generalization of a secant method to higher dimensions. And I've talked about the secant method, which led me to type secant method, when I really meant to type secant condition. Whoops. So what is the secant condition? That AK of xk minus xk minus 1 is equal to f of xk minus f of xk minus 1. All right. Now, imagine this in one dimension. I could divide by this difference, xk minus 1. So what do I have? F of xk minus f of xk minus 1 over xk minus xk minus 1. But that is an approximation of the Jacobian at xk. Oh, wait, I have to be careful about that. So AK is an approximation of a Jacobian at xk, at least along the direction of this difference of vectors here. So in one dimension, I'd be saying that AK is approximately the derivative. So at least in this one-dimensional subspace, in other words, because A times a change in X is equal to a change in Y, along this one direction, AK is approximating the derivative or Jacobian matrix of F. So we're taking this one-dimensional slice of the space and saying it approximates the derivative there. Okay. Now the other condition is that if a vector z is orthogonal to this same direction, then AK times z is equal to AK minus 1 times z. All right. So that means it's approximating so this approximate Jacobian keeps what the previous Jacobian was doing. Now, as the iterates are all converging, hopefully, to a root, this would be a pretty good approximation of a true Jacobian anyway. All right. Now, the reason why I pose these two conditions is that it gives me relatively efficient way to not only define AK, but to define AK inverse. So the way this works is, okay, so this is possible by what is called a rank 1 update of AK minus 1 to get AK. So what I mean by a rank 1 update, I'll give a formula. So AK is equal to AK minus 1 plus, okay, I'll be careful with my notation here, because I have this written in the book for specific indices, but I want to use a general index. YK minus AK minus 1 times SK minus 1 over SK minus 1 transpose SK minus 1 times SK minus 1 transpose. Where YK is equal to this difference of F's. So it's just a shorthand for that. These S vectors, okay, is equal to XK minus XK minus 1. Okay. Alright, so that's how those are defined. So a rank 1 update of a matrix is the matrix, the old matrix, plus a vector times a vector transpose. So it's something of this form. So equals A K minus 1, the matrix being updated, plus UK S K minus 1 transpose. So all of this right here, a fraction, that's a vector, which I'm calling UK. So anytime you have matrix plus vector times vector transpose, that's a rank 1 update. Because this term right here, it's a matrix of rank 1. So in other words, its range is a one-dimensional space. The range is all the multiples of UK. So rank 1 updates are quite nice because we have a formula, an explicit formula for the inverse. So AK inverse using the what is called the Sherman-Morrison formula. So a very nice piece of numerical linear algebra to describe the inverse of a rank 1 update. So AK inverse is equal to AK minus 1 inverse. And then, let's see, plus, and what we have here is also a rank 1 update. So it's, okay, SK minus 1 minus AK minus 1 inverse YK. Okay, and then I have SK minus 1 transpose AK minus 1 inverse. Okay, so that's the numerator. And the denominator has to be numbers. It's going to be an inner product. So it's going to be SK minus 1 transpose AK minus 1 inverse YK. All right. So So this part in parentheses is a vector. The denominator is a number. So we have a vector times this, which is a vector transpose. So the inverse of a rank 1 update is another rank 1 update. But now that we have an explicit formula for the inverse, what we can do is to solve AK equals B. So solving a system with this kind of with this matrix, we first solve AK minus 1. Well, actually, okay. All right. Now the solution of this system appears here, here, and also we solve a system involving YK, and this gets reused within the formula. But now that we have the inverse, we can just do matrix vector multiplication with the inverse. Okay. All right. So actually, I'm going to delete this line because it sidesteps my main point. Using only matrix vector multiplication, not Gaussian elimination. Because if you have the inverse, you just multiply by it. Because it's the solution of Ax equals B is X is equal to A inverse B. Now normally we accomplish that using Gaussian elimination, but if you have the inverse already, then just go with it. Go ahead and compute A inverse times B. A matrix vector multiplication, by the way, is order n squared flops, as opposed to Gaussian elimination, which is, as you should remember from before, order n cubed. So right there, we're saving an order of magnitude of the work. So we're using an approximate Jacobian instead of a true Jacobian, but we are cutting the work down by an order of magnitude. So even though each iteration may not be quite as accurate, we'll be doing a lot less work overall. So we may be performing a few more iterations than before, just as Secant method is a little slower to converge than Newton's method is. But it still works quite well in the end. So less overall computation, because what you're saving per iteration makes up for the fact that you may be performing a few more iterations. So the algorithm for Royden's method is in the book, but basically it's all about updating the Jacobian in this manner. So it has to update these vectors and update this inverse. And otherwise, it's performing essentially Newton's method. It's just using this for the approximate inverse Jacobian instead of a true inverse Jacobian. Okay. All right. But I wanted to make you aware of this concept, very important concept of rank 1 updates and the fact that we know the inverse of a rank 1 update. There is actually a generalization of this. If this was not a vector, if these two were not vectors, but instead matrices of a few columns, like suppose this is a matrix of 4 columns, and then Sk-1 is also a matrix of 4 columns, then it's a rank 4 update. So however many columns UK has, which has to match how many columns this matrix has too, that's the rank of the update. So Sherman-Morrison formula covers rank 1 updates, but there's a generalization, the Sherman-Morrison-Woodbury formula, that covers rank K updates of the inverse. But rank 1 updates occur very frequently in numerical linear algebra, just because it's a nice way to express certain algorithms and take advantage of the fact that when you have a rank 1 update and you multiply this part by a vector, this is here when the second vector is transposed. I'll write this down here. Dang it. Okay. So the expression UV transpose is called an outer product, a matrix. Whereas if I do the opposite, U transpose V. So here I'm transposing a first vector. Here I'm transposing the second. That is an inner product, a number. However, if I take this outer product, UV transpose, and I multiply that, which is a matrix, by some vector x, and I'll just group it this way because matrix multiplication is associative. What do we have here? It's just a vector u times an inner product. So this leads to a lot of simplification of matrix algorithms by being able to express things as outer products and taking advantage of this property of them. Leads to a lot of efficiencies. In fact, the co-author of the textbook, Amber Sumner, dealt with rank 1 and rank 2 updates in her dissertation, and it's something that was very helpful. Okay, so just as the secant method replaced the true derivative of f with an approximate derivative based on a difference quotient, Royden's method uses an approximate derivative also, approximate Jacobian, based on not a difference quotient because you can't divide vectors, but a system of equations that describes, in a sense, a vector version of a difference quotient. So it's very much the same idea, and it works quite well. Okay, so we'll be using these ideas. They can be helpful for systems of ODEs, especially if we're solving. I'm using implicit time-stepping methods, which because we're coming up on the initial value problems chapter, and also for boundary value problems for ODEs, we could solve it using a finite difference method that leads to a nonlinear system of equations. Well, Shadow, you worked with a linear version, but if it's a nonlinear version, then we need one of these methods, and Royden's method is a good choice for that. Okay, so we'll stick around in case anybody has homework questions, but I see I'm out of time here. So coming up next, well, we have spring break. So if you all come back from spring break, then, oh, I'd budgeted 2 days for this. I'm so not doing that. Especially since I didn't give any problems on it. I don't know what I was thinking. If I'd been getting problems on this, then that'd be one thing. So I'll tell you what. Please try to get some homework done. And when you come back, please try to bring some homework questions to help you get it done. At least some of you. And then I may start getting into chapter 12 then. So, okay.